All right, I'm recording. Great. So from what I'm following is yes, there is a way you can move those electrons over there to make that positive charge. And then you would have something like this. However, it's very important to note that you have positive charge here. When you made that resonance structure, do you have that positive charge? That's super important.
No, I didn't. So for the
Make sure you
first
have that
one,
positive.
I moved like both of them at the same time.
Yeah, see, in class and in the recording, the biggest tip he has is moving one step at a time. And my biggest tip for you guys, just straight up when you're approaching these, is whatever charge you have at the beginning, any resonance structure you have has to have that net charge. So for this compound in general, your net charge is just a -1. So for this net charge, it also has to be -1. And you see, wherever you create a negative charge, there has to be a positive charge that cancels it out because you have that negative charge there. Just like how we have in hold on, in this problem, we have a net charge of +1. So whatever minute move you have has to ensure that the things are balanced. And it's a good idea, like I see it at, okay, if I have a system of right sp2 sp2 sp2, let me just move them around in one fell swoop like this, like that. That is valid, but from your case, there's not really anywhere else you can go with that. And that's like the tricky thing he was trying to pull on you guys for this certain question. But again, the thing here, what's the net charge on this one? It's -1. Caitlin, does that answer your question regarding this?
Yeah, it does. Thank you.
It's something you have to look out for. Now that we have some people here, maybe I can start going over the moves and just basically the tips and tricks regarding our problem set. Because going back to here, the main issue I have, or main problem I have with people, is they're putting like double bonds down here. And the biggest thing I have to emphasize is there are cutoff points that you cannot encroach on. Because right here you have sp3 carbons. Okay. And these have hydrogens on them. That's something you can't really see with Kuklay structures, and that's something you really have to look out for. Because if you have a double bond here, well, that's now sp3d, which we can't really have for carbon. And we can't just get rid of the hydrogens, or else that would have a reaction. We can't do that on its own. So it's not really resonance structure. So let's go over the moves. The easiest one is like a door hinge kind of thing. This double bond flips over here, and then whatever carbocation or carb anion charge, formal charge, just flips over. So your new resonance structure is something like this. And that works for negative charge as well. So if you had like a super complex structure like this, this can switch over there. Also charge now here, and then same for this over here. Here, here, and here. Now your positive charge is over there. The door hinge move is super, super nice. Something you should get very used to. Looking at this, which one is the most stable out of the three? There's two of them. Maybe go ahead. Thanks. Okay. I'm pulling up chat right now. If you guys want to put it in chat, you're also welcome to do that.
Be the first two, right?
Yeah, the first two is right now. Since all of these are all the same atom, you're looking at this substitution pattern: secondary, secondary, and primary. You want the charges to be on secondary because secondary atoms, because they can hyperconjugate. Any hydrogens floating around here, they'll somewhat like conjugate and stabilize that to the best of their ability. Secondary is not ideal, but it's better than primary. The next thing is looking at very electronegative atoms. If they have lone pairs, they can donate them into a system. The thing here, you cannot add electrons just willy-nilly, because right here you have atoms that are sp3, so there are hydrogens there. You can't just conjugate and make pi bonds out of them. However, if this is sp2, that's an sp2 carbon because it's missing a pi orbital, you can donate that. So we have something like this. And look right here, we have a positive charge and then a negative charge. Net charge of -1. Nope, not -1, 0. And then net charge right here, again, we have 0. It's like, hopefully that's making a little bit of sense. And now we can probably take a crack at something like this. Okay, so right here we have a recycle hexadiene kind of deal. And we just have a bunch of pi electrons. Now, the thing to note about this, all right, well, look at this. We have a conjugated system, sp2, 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 and sp2. However, this one is sp3. It's also sp2. This sp3 carbon doesn't play a role in conjugation at all. So if you had, for example, something like this, right? You have an sp3 carbon here. So this carbocation cannot skip over more than one carbon, because if this were to door hinge down here, it would form here. It would be nowhere, or this pi bond would be nowhere near that carbocation. So it can't just jump like that. Alternatively, what we can do is if we had a carbocation right there, this pi bond is right next to it because we have an sp2 here, and we can do a door hinge maneuver. Let me erase this. Door hinge maneuver over there and move that pi electron right there. So that's just what I'm trying to show with keeping everything sp2. And hopefully you guys are seeing a pattern. Now that we know all these sp2 carbons, we can start making some resonance structures. And for this specific type of problem set, they don't have to be good resonance structures. They can be something super unstable like this. It's a valid resonance structure. It's just not going to contribute to the hybrid model in nature. Like, it can exist, but it's probably going to be like a nanosecond of that structure is like, I don't know, time in existence. It's not going to be very common. Yeah. So going back to this, all right, well, we don't have any charges we can move around. However, we can move some pi bonds around because we have an oxygen here. We can't door hinge any of these pi bonds yet. However, we can lump it onto that oxygen. And again, one step at a time. We don't move like a lone pair and a pi bond in the same move. It's a good idea to just do one step at a time. So if we move that one pi bond up there, don't forget your formal charge, we would have a compound like this. And again, look at the pattern. Net charge of 0. Let me erase this so you guys can take a better look. Right? We have a net charge of 0. And again, right here, we have a net charge of 0. There's that negative, and you have that positive. Again, whenever you make a negative charge or lump some kind of positive negative charge onto a certain atom, you have to have a counter charge to maintain that. Because wherever an atom loses electrons, one has to gain it. So if you had like an alkene like this, you're more than welcome to lump all of these atoms onto that one carbon to the point where you have something that looks like this. Nope, not that. This. Like that. Again, the net charge is 0, but that's entirely possible. Not really common, but something good to know for resonance structures. All right, let me remove the pink around here. And now we have that negative charge there and that positive charge here again. Now we have some more stuff to work with because these charges can move around with our, again, door hinge maneuvers. So we can move this pi bond over there. if we were to have that, we would have pi plus charge here. And like that. Now, again, look at the charges, -1, +1. Our net charge is still 0, so it gets my thumbs up. Now, there's one more resonance structure, but where can we go? Like this pi bond can't really go all the way over there. Well, the thing is, we can make another resonance structure from that one. What if we were to instead go from this? So we went from that pi bond instead, we would have a compound that looks like this. And again, your final check should be the net charge. It's 0, just like all the others. Is that making a little bit of sense? Or is everyone following?
Yep.
Right. And now let's introduce some heteroatoms. So that was just something like I was drawing. The heteroatoms introduce a lot more complicated stuff. But once you get it, you kind of get it. By the time you get to second semester, you're pretty much going to be a master at residence. It's going to be one of the easy questions on the test. So right here we have, all right, sp3, but it can donate electrons. But right here we have sp2, sp2, sp2. And we have a system because they're all next to each other. There's no sp or sp3 carbons that interrupt anything. Something I saw that I would refrain against is if you have like a lone pair and then an alkene next to it, you can't donate those electrons just yet because, well, then you would have something like this where you have carbon and then double bond there. And then that hydrogen now is still there. That's 5 bonds. You can't overload a carbon, nor can you add lone pairs to an alkene to make an alkyne, because you're changing the hybridization. If you change an alkene to an alkyne, well, you're making sp carbons rather than sp2. So the key hybridization for resonance is sp2. So for this structure, let's just take a little gander. So we know that the net formal charge is, again, 0. Now we can take a look at some valid resonance structures. Let's make some moves. So looking at this straight up, we have 2 formal charges and we have some electrons that we can move around. Well, first off, we cannot move those electrons down there because this is already sp2. If we moved it down there and made a double bond, that carbon would have 2 double bonds and 1 sigma bond. Those are 5 bonds in total, and carbon cannot have that many electrons in its octet. So what if we were to look at this positive charge? Well, we can do something with that. We can door hinge that pi bond over there. Oxygen, nitrogen. Which carbon would that positive charge be? 1, 2, or 3?
Three.
Yeah, it would be a 3.
Everything's finally clicked.
Yeah, I just saw your message. Positive charge would be right there. Now that the positive charge is here, we can make a lot more resonance structures. Now, actually, no, I'll get to that later. We have 2 spots where resonance structures can form. We have a double bond that can form between that carbon, the oxygen, or the nitrogen, because both of them have lone pairs that can donate. Now, real quick, the net charge is, look at it, 0. If we were to move it up to the oxygen, let's go ahead and try that out. NH2, that oxygen right there. Now that we did that, look at that. That is a very valid resonance structure. We still have our sp2 carbons. Our net charge is 0. There's no formal charges at all. Now, what if we were to take a look at that carbon-nitrogen bond? We would have something like this. Don't forget the formal charge there. There we go. Something like that. And look at the formal charges. That adds up to 0. So you have a total of 4 resonance structures there. Now the real kicker is asking you which one is the most stable. Now, looking at this at a glance, which one looks the most stable? 1, 2, or 3?
2.
Yes, actually. Some people might think 1 because, well, look at that. We have a tertiary carbocation. Well, the trick to look at the most stable, there's one main rule you have to look at. So if you're taking notes, write this one down. So the most stable, first of all, the most number of bonds. Because molecules, whichever resonance structure has the most amount of bonds is the most stable. Because rather than having formal charges or dumping a bunch of electrons on an electronegative atom, electrons are in a pretty stable form in a bond. So the more bonds it has, the more stable it is. So look at this. We have one bond, or pi bonds, the most pi bonds. One bond, one pi bond, 2 pi bonds, and 2 pi bonds. So it's either going to be one of these compounds. Now let's look at the formal charges. Number 2 does not have any formal charges, while number 3 has formal charges that are relatively close to each other. So it's kind of easy. This one is the most stable. Now, there's one last thing we have to cover in regards to the most stable. What if you had something where, all right, hypothetically, let's create a situation where we have a carbocation. Ooh. Something like this. Let's have an ether. And then let's have an group. And let's just make an imaginary long compound. All right. Now the 2 possible resonance structures here. Let's make one blue and let's make one green. So if the green route, let's make that the amine route. So this has a lone pair of electrons that could donate. So there would be double bond there. And then the positive charge would be here, CH3, CH3. And then we would have an ether right here. Again, look at that net charge. Net charge is +1. This net charge is +1. So that checks out. In contrast, we have a blue group, see, ether, H3. However, these electrons go there. So I have a double bond there, and then you have an amine group. I'm just going to write it like that to save some room. Now your positive charge is on that oxygen. Now, wait, first off, +1 charge, still good. Now, which one is the most stable? This one's also really tricky that you might see on the test. So these have an equal number of bonds. So that's the first thing you look at. But what if they have, or the most amount of double bonds? If they're equal, now what do you look at? Well, you have to look at where that positive charge lies. And for here, you want to look at electronegativity. Negative charges, you want on atoms like a halogen, like chlorine, or iodine, or oxygen. Positive charges, you want on like carbon or nitrogen, because these are a lot more electropositive. That's a term you should know, electropositive. So when you're looking at the positive charges on in oxygen compared to the positive charges of nitrogen, the nitrogen positive charge is a lot more stable because nitrogen can carry that positive charge a lot better than oxygen. Because if you're looking at electronegativity, oxygen is a lot more electronegative. So if you take the what is it? The converse of that? Nitrogen would be the most electropositive. Does that make sense for you guys?
Yes.
Great. So let's take a look. Yeah, these were just little annotations. Okay, so let's take a look at the problem set. Let's just start from square one. So right here, we have a structure right here. So we have sp3. However, right here, sp2, sp2, sp2. And again, we have, sp2. Even though this is sp3, if it's a heteroatom like a nitrogen or oxygen that has lone pairs, it can donate or withdraw electrons. So it's kind of in the system. It can just, it's like a butt end of something. It can still participate, but it doesn't really do much. But if we're looking at these, one resonance structure we can do is, well, okay, what can we do? We can't door hinge that pi bond over there because this already has, this already sp2. It can't be overloaded with two double bonds. Nor can that lone pair go there because you would have something like this. Two double bonds. That's not ideal. Nor can you add electrons there to make an alkyne. However, what we can do, donate electrons over there. So CH3. CH3. O. Negative charge. Now, this drawing is missing something. Does someone want to shout out what it's missing or throw it in the chat?
Positive charge.
Positive charge. Because look at this. The net charge is 0. The net charge before we added that positive charge is -1. They have to add up. So wherever you create a negative formal charge, there has to be a positive formal charge to cancel it out. Just because at the end of the day, look, at the end of the day, the formal charges have to be the same as your starting point, right? If your starting point was +1, all of the other formal charges have a net charge of +1. All right, that's valid. Now let's move it around. All right, well, now we have something to work with. That's still sp2. However, now we can door hinge and basically move it all around as much as we want. So, do you guys see my screen? It's still, why does it say that? I don't know why it says that. I keep looking at the time like, wait a minute. Okay, ignore that. Nitrogen, CH3. Oh, negative charge. Now we have a double bond here, CH3. Now we're still missing something. It's still the positive charge. Again, we door hinge over there. So the positive charge just trades places. And now the total net charge is still 0. The negative and the positive cancel out, just like the net charge for that original one. Now we can make one more resonance structure. That's going to be here. We have a lone pair right next to a positive charge. We can donate that lone pair and work some magic. Negative, CH3, CH3. And again, there's that positive formal charge on that nitrogen. And look at that, the net charge is still 0. Now looking at this, you have to circle the most stable. Which one is the most stable? Well, using our logic, the most stable one has the most amount of bonds. So this ones are automatically out. So is this one, because they only have one double bond. However, let me change back to pink. I like pink. These two have 2 double bonds, so they're pretty favorable. Now, out of the 2, which one's the most stable? Left or right?
Left.
Yeah. Because even though we have, electropositive formal charge on that nitrogen, and then like a negative charge on an electronegative atom like oxygen, well, let's just have no charges at all. Hold on. Okay, there we go. let's just have no charges at all and choose the right one. So that's the most stable. If you guys are following through. Whoops. Let me go back. Double check, make sure everyone's okay. Great. Now going into this one. All right, we have right here SP3, 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 not SP3, SP2. They're all SP2. For these ones, we have SP3, so they have hydrogens on them. Hydrogens, not favorable, not what we want. So we cannot move any double bonds or anything there. And I know we did this before, but we have some new people at it. So let's just go over it again with the new knowledge we went over. So our first thing is to take it one step at a time. We have an electron pair here in that double bond. You can just move it there. Negative, negative. And what's the net charge? -1. You need a positive charge here in order to maintain that net charge of -1. Now we have a positive charge here. Well, this is right next to a lone pair. Lone pairs next to positive charges, or lone pairs next to positive charges are pretty dandy. So you can make a double bond there and then keep this. And again, right here, look, -1. Now, out of these, which one is the most stable?
The third one?
Yeah, the third one. Because, well, let's look at rule number 1. The most amount of double bonds, or the most amount of bonds just in general is the most stable. So it's not this one. So it's either the left or the right one, because we have one pi bond here, one pi bond there. Now let's look at the formal charges. Formal charges want to be on electronegative or electropositive atoms in relative to what charge they are. So negative charges want to be on electronegative atoms, like a chlorine, iodine, bromine, oxygen, or sulfur. And which one's more electronegative? This oxygen or that carbon is going to be the oxygen. So this one's the most stable. Now let's look over here. Now this one kind of throws a little wrench at you because it's two different maneuvers, but they both stem from the same thing. We have a pair of electrons right here. They're right next to a positive charge. That's sp2, as are these carbons. This is sp3, and it can't do anything there. So we can door hinge maneuver right here and make a charge that looks like this. This bond cannot travel over one carbon. So we just have to do it the other way. It'll look something like this. Now, if you flip these around, these will be pretty much the same thing, but it's the concept we're kind of trying to show here. All right. And if we're looking, all right, which one's the most stable? Well, rule number 1, which one has the most pi bonds? All of them do. Which one has the respective formal charges on the most stable atom? All of them do. All of them have positive charges on carbons. Now let's look at substitution. All right, well, if they're on carbons, which one can better accommodate a formal charge? Tertiary carbons are the best ones, but all of these are secondary. If all of these formal charges on secondary carbons, they're pretty much all exactly the same. All of them are equally stable. And if we were to look at the hybrid model, this is what that would look like. All right. Does anyone have any questions regarding resonance structures? Hopefully this went over pretty much everything, answered everything, because it really is just, well, practice. Once you get the hang of it, you're pretty unstoppable.
You have extra practice sets that you can give us?
Yes. I have one problem set that can work, but I don't
I'll take anything, to be honest.
All right, let me go ahead and stop my share. Stop share and send that in. Let me go ahead and pause the recording. It's not working. That's okay. Let me just go ahead and post it. Are you guys liking the memes on my announcements?
I can tell you're having a lot of fun with them.
I am.
And your profile pics as well.
What's up?
Your profile pics as
Oh
well.
yeah,
I don't know if you saw, I tried doing the same thing, but now Zoom's kind of screwed me up, so I don't have a last name anymore, apparently. I don't know what's going on.
Damn. I I find some pretty rancid memes. The Sonic one, I was so funny. Sonic, please bounce. Okay, okay. I'm done. I'm done. Okay, I posted another problem set in the group me. That's the only other one I have because I think all the other ones are pretty much the same. Do you guys have any last minute questions? I think the one I posted deals, there's a deals all question at the bottom. We haven't learned that yet. And I don't think it shows up in any of your future problem sets. But if you guys want to hold on to it and just wait until after we learn the deals all reaction, you can give it a shot. Other than that, that's pretty much all I wanted to go over. Julia, I am recording this. So don't worry if you missed anything. I'll post it pretty shortly.
Yeah, thank you. Sorry, I just had to get in through like my phone and then join back on the computer because it was just messed up. But
Oh, good.
everything's good. So thank you for recording anyhow.
Sweet. Well, were you able to watch or witness most of the content?
Yeah, and I was like applying the stuff that you said before. We went over the homework, so it's all good. And if
Great.
I need to, I can just go back. So thank you.
Yeah. And for future reference, we've been pretty, nah, not yet. I'm not going to say that just yet. Someone post in chat. Do you have the answer keys to the 2021 test you sent? Yeah, I am preparing. Oh, yes, I think so. I'm not gonna post it, but Brianna, if you just want to email me, I can email you the stuff.
I'm just so happy it finally clicked.
Yeah. It was,
I was muted, but I started because problem was the only one I had left. You didn't even start the practice example that was similar to the first one, but I just saw it and I just went, wait a minute. Yes.
Yeah.
And then as you were actually going through it, I just sat there going, oh, thank God. I got it. Finally.
Yeah. For the final, I have this document, all right. When I was studying for the OChem 1 final, I just basically downloaded all the tests and they were all the 2021 tests. And I just basically call it like the final exam boot camp, where I just went over every single test. And it was pretty effective. So I can probably post that leading up to the final. Yeah, unfortunately, your week of the final, I will be out of town. So I don't think I'll be able to hold a review session for the final, but I will post plenty of resources and I'll answer emails normally. But yeah. Does anyone have any questions about the problem set 9, or any content questions? Throw them out, or about the test?
I have a question that I don't know if you'll be able to answer. I could just email Dr. Berg. But for like the second portion, like the equivalent to the second semester of this class, is Dr. Berg not teaching it? Because I'm signed up for another like asynchronous person online.
Are you talking about the summer session?
Yeah, the summer session.
Yeah, there's a different professor. I don't think Dr. Berg is going to teach second semester.
Okay, just making sure if I was like missing something, but
yeah. In my opinion, once you get used to OChem 1, that's kind of like the big hurdle on why like OChem is pretty hard, because it's just like you haven't gotten the groove of your stuff yet. But OChem 2, the material is a little harder, but like you're kind of an OChem veteran where you know what you're trying to look for and the habits you have. So I found second semester a lot easier.
Okay, cool. Thank you so much.
Yeah.